Right now, a spacecraft no larger than a compact car is transmitting signals from a place no human-made object has ever reached before it. Those signals take more than 22 hours to arrive, travelling at the speed of light, crossing a distance so vast that the number that describes it requires scientific notation to write cleanly. The spacecraft is Voyager 1. It launched in September 1977, and it's been moving outward every single second since then, through the asteroid belt, past Jupiter, past Saturn, past the orbit of Pluto, past every planet and moon and known body in our solar system, until it arrived at something that scientists had theorized for decades but never been able to directly confirm existed. A boundary, an actual physical edge where the sun's influence ends and something else begins. On August 25, 2012, Voyager 1 crossed that boundary. What it detected there was not what anyone predicted, and what it revealed about the edge of our solar system is something that fundamentally rewrites what we thought we knew about where we live. The sun is not quiet. It has never been quiet. Every second of every day, it erupts outward in all directions with a constant stream of charged particles, a plasma wind blowing at speeds between 250 and 750 kilometers per second, carrying the sun's magnetic field into the surrounding space, like a bubble being inflated in all directions simultaneously. This is called the solar wind, and it fills an enormous region of space known as the heliosphere, a vast magnetic bubble that surrounds the entire solar system and extends outward in every direction like a force field generated by the sun itself. For most of human history, no one knew this region had a boundary. The idea that the sun's influence simply ran out, that there was a place where the solar wind stopped and the rest of the galaxy began, seemed almost too clean, too defined, for a universe that resists definition. But that boundary exists. It is real. It has been measured. And the things NASA detected at that boundary are stranger, more violent, and more revealing than anyone anticipated. The boundary is called the heliopause. It is not a wall. It is not a solid surface you could touch or see or photograph from any reasonable distance. It is a region of transition, a zone where the pressure of the solar wind finally equals the pressure of the interstellar medium, the gas and plasma that fills the space between star systems, and where the two forces come to a standoff that marks the outer edge of everything the sun controls. Beyond it, the sun has no influence. The magnetic field it created for billions of years, the one that has been quietly deflecting cosmic radiation and shielding the planets inside it, stops at that line. Beyond it, you are no longer in the sun's solar system in any meaningful physical sense. You're in interstellar space, drifting in the galaxy itself. Voyager 1 crossed that line, then Voyager 2 crossed it 6 years later. And what both spacecraft detected at that threshold, and just beyond it, revealed something about the architecture of our solar system that scientists are still trying to fully interpret. If you enjoy documentaries that go deep into the science behind the biggest discoveries in space and reveal the full story that most coverage never reaches, do me a favour and hit that like button and subscribe. It genuinely helps this channel grow and lets me keep making these deep dives for you. Every subscriber makes a real difference, and I appreciate each one of you more than I can say. Now settle in and get yourself comfortable. We are going to the edge of the solar system together. Let's begin. The story of the heliopause begins with a prediction that was almost never made. In 1958, a young University of Chicago astrophysicist named Eugene Parker submitted a paper to the Astrophysical Journal proposing something that the scientific community considered almost absurd. Parker argued that the sun was not simply sitting there radiating light and heat. He argued that it was continuously blasting charged particles outward into space in all directions, a constant supersonic stream of electrons and protons that he called the solar wind. This was not an observation. Parker had no data from beyond Earth's atmosphere because no spacecraft had yet travelled there to measure it. He was working from theory, from the mathematics of plasma physics and thermodynamics, from the equations that described how a hot, dense stellar corona would expand outward if the universe gave it somewhere to go. The paper was initially rejected. The editor who reviewed it, a distinguished astronomer, described the concept as physically impossible and found the paper not worth publishing in its current form. Parker was told to revise. The editor who nearly killed the solar wind theory was Subrahmanyan Chandrasekhar, one of the most celebrated astrophysicists of the 20th century. Chandrasekhar had already made foundational contributions to stellar evolution and would go on to win the Nobel Prize in Physics in 1983. He was not a minor figure. He was the gold standard of credibility in the field. When Parker received the rejection, he could have accepted the verdict. The scientific community's consensus was against him. Most astronomers believed that the region between the Sun and the stars was essentially empty, perhaps punctuated by the slow diffusion of gas, but certainly not swept by a continuous supersonic wind of plasma. Parker did not revise his theory. He responded to Chandrasekhar's objections directly, defended his mathematics, and eventually the paper was published. That paper, titled Dynamics of the Interplanetary Gas and Magnetic Fields, appeared in 1958 and introduced the concept of the solar wind to the scientific literature. 2 years later, the Soviet Luna 1 spacecraft made the first in situ measurement of solar plasma near Earth. Parker was correct. The solar wind was real. The confirmation came faster than anyone expected. Luna 1, launched by the Soviet Union in January 1959, passed by the Moon and continued outward into interplanetary space. Among its instruments was a detector designed to measure the density of charged particles in the region between the Earth and the Moon. It detected them. It detected a continuous, measurable stream of ions and electrons moving outward from the Sun at high velocity. The result was ambiguous enough that the scientific community did not immediately declare the solar wind confirmed, but the signal was there. The cleaner confirmation came from the American Mariner 2 spacecraft, launched in 1962 on a trajectory toward Venus. Mariner 2 carried 2 separate plasma detectors, and both of them measured the solar wind continuously throughout its 109-day journey. There was no ambiguity. The solar wind was not an occasional phenomenon. It was permanent. It was continuous. The Sun was constantly, ceaselessly blasting the entire solar system with a stream of charged particles moving at hundreds of kilometers per second every day, without pause, in every direction at once. To understand what NASA detected at the edge of the solar system, you first have to understand what the solar wind actually is at the atomic level. The Sun's corona, its outermost atmospheric layer, reaches temperatures above 1 million degrees Kelvin. This is paradoxical and still not fully understood. Since the visible surface of the Sun, the photosphere, is only about 500 degrees Kelvin. Why the outermost layer is hundreds of times hotter than the surface below it is one of the most persistent mysteries in solar physics. But regardless of why, the effect is clear. At 1 million degrees, plasma cannot stay bound to the Sun. The thermal energy of the particles exceeds the gravitational energy holding them in place. They escape. They pour outward in all directions, electrons and protons and heavier ions all streaming away from the solar corona at velocities that range from 250 kilometers per second during quiet periods to 750 kilometers per second or more during solar eruptions. By the time this wind reaches Earth, it has thinned dramatically, but it is still there, still moving, still carrying with it the Sun's magnetic field like iron filings frozen in the flow. As this solar wind streams outward, it creates a structure in space. The structure is the heliosphere. Think of it as an enormous magnetic bubble, a region of space dominated by the sun's magnetic field and solar wind plasma, rather than by the interstellar magnetic field and gas that fill the galaxy beyond it. This bubble is not spherical. The solar system is not sitting still in space. It is moving through the galaxy at approximately 70,000 kilometers per hour, sweeping through the local interstellar medium as it travels. The pressure of the interstellar medium pushing against the forward-facing side of the heliosphere compresses it, while the backward side stretches out into a long tail, like the wake behind a ship. The result is a shape something like a comet, blunt and rounded on the nose and drawn into a long tail pointing away from the direction of travel. The entire solar system, all 8 planets, the asteroid belt, the Kuiper belt, all of it sits inside this bubble. The boundary of that bubble is the heliopause. Everything inside it is, in a very real physical sense, inside the sun. How big is this bubble? The answer requires context to be meaningful. The Earth sits approximately 1 astronomical unit from the Sun. 1 astronomical unit is roughly 150 million kilometers, the average distance between the Earth and the Sun. Mars sits at about 1.5 astronomical units. Jupiter at 5.2. Neptune, the outermost planet, orbits at about 30 astronomical units. The Kuiper belt, the vast ring of icy bodies and dwarf planets that includes Pluto, extends to approximately 50 astronomical units. The heliopause, the actual outer edge of the heliosphere where the solar wind finally stops, sits at roughly 120 astronomical units in the direction the solar system is moving through the galaxy, and possibly 200 or more astronomical units in the trailing direction. To put that in perspective, Neptune, the 8th planet, is at 30 astronomical units. The heliopause is 4 times farther out than Neptune. The edge of the solar system in the most physically meaningful sense, the place where the sun's direct influence ends, is 4 times farther away from the sun than the most distant planet. In kilometers, the heliopause in the upwind direction sits at approximately 18 billion kilometers from the sun. 18 billion kilometers. The fastest jet aircraft ever built, the SR-71 Blackbird, had a top speed of about 300 kilometers per hour. At that speed, travelling without stopping, it would take that aircraft more than 587,000 years to reach the heliopause. Light itself, travelling at 300,000 kilometers per second, takes more than 16 hours to get there. The radio signals that Voyager 1 transmits back to Earth, travelling at the speed of light, take over 22 hours to make the journey home. When mission controllers at NASA's Jet Propulsion Laboratory send a command to Voyager 1, they wait 4 hours before receiving any confirmation that the spacecraft received it and responded. This is not a human-scale distance. It is not a solar system-scale distance in the way most people understand that phrase. It is the outer boundary of everything the sun controls, and it is so far away that our most reliable reference points for comprehending large numbers begin to break down. Before we follow Voyager to the edge, it is worth noting what happened to the man who first predicted the wind that fills the heliosphere. Eugene Parker spent his career at the University of Chicago. He continued working on solar physics for decades, contributing fundamental theoretical work on the behavior of magnetic fields in stellar atmospheres and the dynamics of cosmic rays within the heliosphere. He was not fully vindicated in the way discovery stories usually go, not with a single dramatic moment of proof, but through a gradual accumulation of evidence from every spacecraft that passed through the inner solar system. By the time Parker was in his 90s, still publishing research papers, the solar wind he had predicted in 1958 had been measured by hundreds of instruments on dozens of spacecraft. In 2018, NASA launched a mission specifically named in his honor. The Parker Solar Probe is the fastest human-made object ever built, designed to fly closer to the Sun than any previous spacecraft and measure the solar corona directly. Parker was there for the launch. He was 91 years old. The probe carries a photograph of him and a copy of his 1958 paper. Reaching the heliopause required a spacecraft capable of travelling farther than any human-made object had ever travelled before, and surviving long enough to get there. This was not obvious when the Voyager program began. The primary mission of Voyager 1 and Voyager 2 was to study the outer planets. Voyager 1 launched on September 5, 1977, and Voyager 2 launched 16 days earlier on August 20th, though Voyager 1 was on a faster trajectory that would allow it to overtake its twin. The twin probes were designed to exploit a rare alignment of the outer planets, a configuration that occurs only once every 1 to 5 years and allows a spacecraft to use the gravity of each successive planet to slingshot itself to the next. This grand tour trajectory would allow a single mission to visit Jupiter, Saturn, Uranus and Neptune in sequence, using planetary gravity as a free acceleration system. The alignment window opened in 1977 and would not return until 2053. The Voyager program was built to catch it. The journey to the heliopause was a bonus, an afterthought almost, an extension of a mission that was originally designed to last until Saturn. Both Voyager spacecraft delivered extraordinary returns during their primary mission phases. Voyager 1 reached Jupiter in March 1979 and returned the first clear images of the volcanic eruptions on Io, revealing that moon as the most geologically active body in the solar system. It measured the plasma torus that encircles Jupiter along its magnetic equator. It resolved the cloud bands of the giant planet with a clarity that ground-based telescopes had never achieved. Then it flew onto Saturn, arriving in November 1980 and making the first detailed measurements of the ring system and the magnetic field. After Saturn, Voyager 1 used the gravity of Titan, Saturn's largest moon, to execute a trajectory change that boosted it up and out of the plane of the ecliptic, putting it on a path that would eventually carry it out of the solar system in a northward direction relative to the plane of the planets. This trajectory change ended any possibility of visiting Uranus or Neptune, but it put Voyager 1 on the most direct path toward the interstellar boundary. From that moment, Voyager 1's destination was no longer another planet. It was the edge. In February 1990, as Voyager 1 was crossing the outer reaches of the solar system and still had decades of travel ahead of it before reaching the heliopause, Carl Sagan proposed that the spacecraft should turn its cameras back toward the inner solar system and take a photograph of Earth from the far side of space. The spacecraft was already beyond Neptune, at a distance of approximately 1 billion kilometers. Controllers at JPL debated whether the maneuver was worth the risk. The cameras had been powered down to conserve electricity. Reactivating them would consume resources. Sagan argued that the image had no scientific value, that no data would be gained from it, but that it had profound human value, that seeing Earth from the outer edge of the planetary system would give humanity a perspective it had never had before. They turned the camera on. The resulting photograph showed Earth as a faint point of blue light, less than a pixel in size, suspended in a beam of scattered sunlight against the darkness. Sagan's description of that image, the pale blue dot, contains some of the most important words written in the 20th century, but they came from a spacecraft still well inside the solar system. Voyager had a very long way still to go. The region between the planetary orbits and the heliopause is not empty. It is filled with the extended tail of the solar wind, thinning as it travels farther from its source, but still moving, still carrying the sun's magnetic field. This region, everything from the outer planets outward to the heliopause, is called the outer heliosphere. Within it, the solar wind is moving supersonically. The speed of sound in a plasma is not the same as the speed of sound in air. It is determined by the magnetic field strength and plasma density rather than pressure and temperature alone, but the principle is similar. Just as an aircraft exceeding the speed of sound creates a shock wave, the solar wind moving supersonically through the outer heliosphere must slow down somewhere before it reaches the heliopause. The transition where it does so is called the termination shock. The termination shock was the first major boundary the Voyager spacecraft had to cross before reaching the heliopause itself, and crossing it turned out to reveal something unexpected about the shape of the heliosphere and the nature of the transition zone lying between the termination shock and the outer edge. The termination shock is a boundary where the solar wind transitions from supersonic to subsonic flow. Before the termination shock, the solar wind is moving outward at hundreds of kilometers per second, faster than the speed at which pressure waves can propagate through the plasma. When the solar wind hits the termination shock, it slows abruptly. The kinetic energy of the fast-moving plasma converts into heat. The plasma becomes denser, hotter, and turbulent. It is still moving outward, still heading toward the heliopause, but now at subsonic speeds, shuffled and stirred and disorganized in a way it was not before. The region between the termination shock and the heliopause, where this hot, slow, turbulent solar wind plasma stacks up against the outer boundary, is called the heliosheath. Think of it as the rind of the heliosphere. The planets sit in the smooth interior, where the solar wind is fast and relatively orderly. The heliosheath is the messy outer layer, where the wind has slowed and the plasma has become dense and hot and chaotic. To reach interstellar space, Voyager had to cross the termination shock, traverse the heliosheath, and then cross the heliopause itself. Each crossing revealed something new. On December 16, 2004, at a distance of approximately 4 astronomical units from the Sun, Voyager 1 crossed the termination shock for the first time. This was the first time any spacecraft had ever entered the heliosheath. Mission scientists could tell the spacecraft had crossed the boundary because of a sudden change in the behavior of several instruments simultaneously. The magnetic field strength increased abruptly. The speed of the solar wind dropped. The density of energetic particles changed dramatically. One of the key instruments used to confirm the crossing was the low-energy charged particle detector, operated by Stamatios Meegis and his team at the Johns Hopkins Applied Physics Laboratory. They'd been watching the behavior of anomalous cosmic rays, a particular type of energetic particle that originates when interstellar neutral atoms are swept up by the solar wind and accelerated. The expectation was that these anomalous cosmic rays would peak in intensity at the termination shock, the place where their acceleration was theorized to occur. They did not peak. Their intensity barely changed. This was deeply puzzling. Either the termination shock was not where these particles were being accelerated, or the theory was wrong. The heliosheath was already showing its complexity before Voyager had finished crossing into it. Nearly 3 years after Voyager 1 made the first termination shock crossing, Voyager 2 made its own. On August 30, 2007, at a distance of approximately 4 astronomical units from the Sun, Voyager 2 entered the heliosheath. The fact that Voyager 2 crossed at a slightly shorter distance than Voyager 1, despite travelling in a slightly different direction, was itself informative. The heliosphere is not a perfect sphere. Its shape varies depending on which direction you are measuring. The difference in crossing distances between the two spacecraft, 10 astronomical units despite different approach angles, suggested that the heliopause was asymmetric, that the pressures acting on the heliosphere from outside were not uniform in all directions. More significantly, Voyager 2 had a working plasma science instrument that Voyager 1 did not. The plasma science instrument on Voyager 1 had failed in 1980, before the spacecraft even reached Saturn. Voyager 2's plasma instrument was still functioning, which meant for the first time ever, scientists had direct in situ measurements of the plasma conditions inside the termination shock and throughout the heliosheath, not inferred from secondary instruments but directly measured from a probe moving through the material. What Voyager 2's plasma science instrument found in the heliosheath was striking and strange. The solar wind plasma in the heliosheath was not smoothly distributed. It was turbulent, variable, and filled with fluctuations in density and temperature that seemed to defy easy explanation. The plasma temperature was far higher than theoretical models had predicted. Some of the excess heat appeared to come from pickup ions, interstellar neutral atoms that had drifted into the heliosphere and been ionized by sunlight or by charge exchange with solar wind protons, becoming energetic particles that contributed unexpectedly large amounts of kinetic energy to the plasma flow. The direction of the plasma flow was also surprising. Rather than moving smoothly outward and then deflecting along the heliopause, the plasma in the heliosheath appeared to be moving in complex multi-directional flows that included significant components running perpendicular to the radial direction from the Sun. The heliosheath was not behaving like the simple buffer region that early models had predicted. It was a dynamic, churning, magnetically complex environment in which the boundary between the solar system and interstellar space was being actively negotiated on a continuous basis. Voyager 1 spent nearly 8 years travelling through the heliosheath after crossing the termination shock in December 2004. Throughout those years, it was still inside the heliosphere, still in the region dominated by the solar wind, but in a transformed version of it. The solar wind it was moving through was slow, hot, and disordered, nothing like the clean supersonic flow it had measured for the previous 27 years. Mission scientists were using the data from the cosmic ray subsystem, a particle detector operated by Edward Stone's team at Caltech and JPL, to track the ratio of anomalous cosmic rays to galactic cosmic rays. Galactic cosmic rays are high-energy particles that originate from outside the heliosphere, produced by supernovae and other violent events in the galaxy. The heliosphere acts as a partial shield against them, so their intensity inside the heliosphere is lower than it is outside. Anomalous cosmic rays are different. They originate inside the heliosphere from accelerated interstellar neutrals. The expectation was that as Voyager 1 approached the heliopause, galactic cosmic ray intensity would rise, and anomalous cosmic ray intensity would peak and then drop once the spacecraft exited into interstellar space. Monitoring those two populations became one of the primary methods of tracking how close Voyager 1 was getting to the boundary. In the months leading up to August 2012, Voyager 1's instruments recorded a series of dramatic and puzzling particle flux changes that seemed to indicate it was crossing the heliopause, only for the readings to reverse and return to near heliosheath levels. Between July and August of 2012, the instruments recorded sharp drops in an anomalous cosmic ray intensity and corresponding rises in galactic cosmic ray intensity consistent with what would be expected at the heliopause, but then the changes partially reversed. The magnetic field direction, which scientists had been monitoring as another indicator of the heliopause crossing, did not change during these events in the way that crossing into interstellar space would require. The team began to suspect that Voyager 1 had entered a novel region not clearly predicted by existing models, a zone where the solar wind particle populations were behaving like the interstellar side of the boundary, but the magnetic field was still connected to the solar side. Some scientists propose calling this region the heliocliff. Others propose that the heliopause was more variable than any model had assumed, moving inward and outward in response to changes in solar activity like a breathing membrane. The mystery of exactly what the boundary looked like from the inside was deepening just as Voyager 1 was about to cross it for good. On August 25th of 2012, all ambiguity ended. The instruments on Voyager 1 recorded a sharp, clean, apparently permanent set of changes that have not reversed in the years since. The count of anomalous cosmic rays dropped dramatically and did not recover. The count of galactic cosmic rays rose sharply and remained high. These two changes had been anticipated, but the magnetic field direction was the key measurement that would definitively confirm whether the spacecraft had exited the heliosphere. Magnetic field lines in the heliosphere run roughly parallel to the ecliptic plane, swept into a spiral pattern by the Sun's rotation. Magnetic field lines in the interstellar medium run at a different angle, roughly 30 degrees offset from the heliospheric field. If Voyager 1 had truly crossed the heliopause, the magnetic field direction measured by its magnetometer should change to reflect the interstellar field rather than the solar field. When Ed Stone's team at Caltech analysed the data from the August 25th crossing, they found that the magnetic field direction had indeed changed by approximately 40 degrees. Combined with the particle data, this was the confirmation. Voyager 1 had left the heliosphere. For the first time in the history of the solar system, a human-made object was in interstellar space. The most dramatic piece of evidence for the heliopause crossing did not arrive immediately in August 2012. It came later, from a completely different type of instrument, and it confirmed the crossing with a kind of precision that silenced any remaining doubt. Don Gurnett and his team at the University of Iowa had built the Plasma Wave Science instrument on Voyager 1. This instrument was designed to detect oscillations in plasma, small wave-like disturbances that propagate through the electron gas at frequencies that depend on plasma density. Inside the heliosphere, plasma density was low, and the frequencies that the instrument detected reflected that. In interstellar space, plasma density should be much higher, and plasma oscillation frequencies should be correspondingly higher. In April 2013, a solar outburst sent an energetic particle wave outward from the Sun. That wave took a year to travel to Voyager 1's location. When it arrived, it excited a plasma oscillation in the material surrounding Voyager 1, and Guyot Arnett's instrument detected the frequency of that oscillation. The measured frequency corresponded to a plasma density 40 times higher than what had been measured inside the heliosphere. That density was consistent with the theoretical prediction for interstellar plasma. Voyager 1 was in interstellar space. The measurement was unambiguous. That plasma density measurement deserves its own attention because it is one of the most informative numbers to come out of the Voyager crossing. Inside the heliosphere, the solar wind plasma near Voyager 1's location had a density of roughly 0.0006 particles per cubic centimeter. The number is almost impossible to imagine. A cubic centimeter is a cube roughly the size of a sugar cube. Inside that cube, in the space the heliosphere creates around our solar system, there would be about 6 10,000ths of a single particle. The space inside the heliosphere is emptier than any vacuum that can be created in a laboratory on Earth. But the interstellar medium, the space between stars, is not quite as empty. Gurnett's plasma density measurement outside the heliopause gave a value of approximately 0.08 electrons per cubic centimeter. That is still incredibly empty by any human standard. A human breath contains roughly 20 billion molecules per cubic centimeter. But compared to the interior of the heliosphere, interstellar space near the heliopause is about 30 times denser. The difference in emptiness between inside and outside the solar system's outer boundary is measurable, quantifiable, and real. The magnetic field measurement told its own story about the heliopause crossing. For the entire time Voyager 1 had been travelling through the heliosphere, its magnetometer had been measuring a field that showed the unmistakable signature of solar origin. The Sun's magnetic field is dragged outward by the solar wind, and as the Sun rotates, this field is wound into a spiral pattern, like the water spraying from a spinning garden sprinkler. The result is a large-scale magnetic field structure throughout the heliosphere that wraps around the Sun in a characteristic Parker spiral named for Eugene Parker, who first described it mathematically. Voyager 1 had been travelling through this Parker spiral field for 35 years. When it crossed the heliopause, the magnetic field direction changed. It did not point in the direction expected for a clean transition to the galactic magnetic field, which was somewhat disappointing to theorists who had predicted a larger angular shift, but it did shift by approximately 40 degrees and showed a new, steady orientation consistent with the interstellar field. The field strength did not change dramatically at the boundary, which was itself informative. The transition was in the field's direction and the particle populations, not in the overall intensity of the field. Here is where the Voyager 1 crossing produced its most scientifically significant surprise, and one that is still being actively studied more than a decade later. The galactic cosmic rays. When Voyager 1 crossed the heliopause, the intensity of galactic cosmic rays increased sharply as expected. These are the high-energy particles originating from violent events across the galaxy, and the heliosphere acts as a partial shield against them. Inside the heliosphere, approximately 70% of incoming galactic cosmic rays are deflected or absorbed before they can reach the inner solar system and the planets. Crossing the heliopause means exiting that shield. The increase in galactic cosmic ray intensity was expected and was indeed observed, but the magnitude of the increase was larger than models had predicted, and the energy spectrum of the cosmic rays outside the heliopause showed features that suggested the galactic cosmic ray environment just beyond our solar system is more complex and more energetic than the models built before the crossing had assumed. The heliosphere had been filtering the cosmic ray environment in ways that models had not fully captured, and the data from just beyond the heliopause offered the first direct measurement of what the galactic cosmic ray environment actually looks like when that filtering is removed. The anomalous cosmic rays told the opposite story. Inside the heliosphere, particularly in the heliosheath, these particles had been abundant. They are formed from interstellar neutral atoms that drift into the heliosphere, become ionized, and are then accelerated by the solar wind to high energies. For years before the heliopause crossing, Voyager 1's instruments had been measuring a significant population of these particles. Theory predicted that when Voyager 1 crossed the heliopause, anomalous cosmic ray intensity should drop, because the mechanism that created them, the interaction of interstellar neutrals with the solar wind inside the heliosphere, would no longer be operating in the spacecraft's immediate environment. The drop happened. It happened abruptly. Within days of the August 25, 2012 crossing, the anomalous cosmic ray count had essentially gone to zero. The particles vanished almost instantaneously on the timescale of the crossing. The speed of that disappearance was faster than some models had predicted, and confirmed that the heliopause was acting as a sharp boundary for this particle population, much more defined and effective as a dividing surface than the murky, turbulent region it had appeared to be from theoretical models built in the decades before Voyager actually crossed it. While Voyager 1 was crossing the heliosheath toward the heliopause, a different NASA mission was revealing an unexpected structure in the outer heliosphere that no one had anticipated. The Interstellar Boundary Explorer, known as IBEX, launched in October 2008 on a small spacecraft built for less than $70 million. was designed to map the heliosphere from the inside by detecting energetic neutral atoms, particles that are created when solar wind protons exchange charges with interstellar neutral hydrogen atoms. These energetic neutral atoms travel in straight lines because they are electrically neutral and are not deflected by magnetic fields, which means they carry directional information about where in the heliosphere they were created. When IBEX scientists created a full-ski map of these energetic neutral atoms in 2009, they expected to find a more or less uniform distribution reflecting the global structure of the heliosphere. What they found instead was a sharp, bright ribbon of concentrated emission that wrapped across a large portion of the sky in a narrow arc. The ribbon was completely unexpected. It was brighter than any existing model had predicted for any region of the sky, and its shape and location did not correspond to any known boundary in the heliosphere. The IBX ribbon immediately sparked debate about its origin. It is roughly aligned with the direction of the local interstellar magnetic field, the magnetic field that threads through the space our solar system is moving through. But the mechanism that would concentrate energetic neutral atom emission along that alignment was not obvious. Several competing theories were proposed. One explanation involves solar wind protons that travel outward through the heliopause, exchange charges to become neutral, travel some distance into the interstellar medium, then exchange charges again, become ionized, gyrate around the interstellar magnetic field lines, and eventually exchange charges a third time to become neutral atoms that travel back toward the inner heliosphere where IBEX can detect them. The geometry of this three-step process would produce a ribbon roughly aligned with where the interstellar magnetic field is perpendicular to the line of sight from the Sun. The ribbon appears to be located where that condition is met. This process, if confirmed, would mean that the IBEX ribbon is essentially a tracer of the interstellar magnetic field architecture surrounding our solar system, a map of the magnetic environment through which our solar system moves, drawn for us by our own solar wind particles as they bounce off the boundary. IBEX also made a second major discovery that reshaped understanding of the heliosphere's overall shape. By mapping the distribution of energetic neutral atoms across the entire sky over multiple years, the IBEX team was able to construct a picture of the full three-dimensional structure of the heliosphere, including the heliotail, the long trailing structure that extends behind the solar system as it moves through the galaxy. This heliotail had been predicted theoretically for decades, but its actual shape and structure had never been observed. The IBEX maps revealed that the heliotail is not a simple, smooth extension of the heliosphere. It is divided into two lobes of different particle energies, separated by a region of slower-moving material in the middle. The high-energy lobes extend above and below the plane of the ecliptic. The slow-moving central region extends more or less in the plane of the planets. This structure suggested that the heliosphere's tail is being shaped by the interaction of the solar wind with the local interstellar magnetic field in a more complex way than the models had predicted, with the interstellar magnetic field twisting and confining the tail into a braided, multi-lobed structure rather than a smooth conical wake. The heliotail turned out to be far longer than anyone had expected. Early theoretical models had suggested the tail might extend for a few hundred astronomical units before the solar plasma was mixed into the interstellar medium and the heliosphere effectively ended in that direction. IBEX data suggested the tail might be significantly longer, extending for perhaps 1,000 astronomical units or more. Later analyses, combined with data from the Cassini spacecraft's magnetospheric imaging instrument, which could also detect energetic neutral atoms at high energies, began to paint a picture of a heliosphere whose tail was among the most extended structures in the local region of the galaxy. an enormous comet-like wake behind the solar system that has been building since the solar wind first began to blow more than 4 billion years ago. This tail contains the accumulated record of the solar system's passage through its local galactic neighbourhood. The plasma and magnetic field threaded through it carry information about the history of the solar wind over timescales of millions of years, stretching out behind us like a trail in space that we can, with the right instruments, read backward in time. Beyond the heliopause, Voyager 1 entered a region called the local interstellar medium. This is not empty space in any meaningful sense, although it is extraordinarily tenuous by everyday standards. The local interstellar medium is the gas and plasma that fills the Milky Way galaxy between star systems, the physical material of interstellar space itself. It is primarily composed of hydrogen followed by helium, with trace amounts of other elements. Near the Sun, the local interstellar medium has been identified as a specific structure called the local interstellar cloud, sometimes called the local fluff, a warm, partially ionized cloud of gas and dust that our solar system has been moving through for the past 100,000 years or so. The local interstellar cloud is approximately 30 light-years across, and our solar system sits near one edge of it. The temperature of this material is approximately 6,000 to 10,000 Kelvin, warmer than many models had assumed. Its density, as measured by Voyager instruments, is consistent with what was estimated from observations of neutral hydrogen absorption in the spectra of nearby stars. The heliosphere sits inside this cloud like a bubble inside a warm, thin mist. On November 5, 2018, Voyager 2 became the second human-made object to cross the heliopause and enter interstellar space. It crossed at a distance of approximately 119 astronomical units from the Sun, about 2 astronomical units closer to the Sun than Voyager 1's crossing point despite travelling in a different direction. This asymmetry confirmed that the heliosphere is indeed compressed differently in different directions due to the asymmetric pressure of the interstellar medium. Voyager 2's crossing provided something Voyager 1's could not, because Voyager 2 still had its functioning plasma science instrument. This meant that for the first time, scientists had direct plasma measurements from both sides of the heliopause in close sequence. The plasma data from Voyager 2 showed that the heliopause was very thin, a transition region only a few astronomical units thick rather than the diffuse extended zone that some models had predicted. The transition from solar wind plasma to interstellar plasma was sharp, not instantaneous, but sharp enough to be measured in a matter of days rather than weeks or months, reinforcing the picture of the heliopause as a genuine, well-defined boundary rather than a fuzzy, gradual blending of two environments. One of the most striking measurements from Voyager 2's heliopause crossing came from the plasma temperature data. Inside the heliosheath, the solar wind plasma was hot, having been heated by the termination shock crossing to temperatures of approximately 100,000 to 200,000 Kelvin. This was warm plasma by interstellar standards, but at the heliopause crossing the temperature dropped sharply. The plasma outside the heliopause, the interstellar plasma, had a temperature of roughly 30,000 to 50,000 Kelvin. This was actually expected from theory, but the sharpness of the temperature transition confirmed that the heliopause was doing exactly what the model said it should do, preventing the solar plasma from mixing freely with the interstellar plasma. There was a boundary layer, a thin zone where both plasma populations were present and mixing was occurring, but it was narrow. On one side, hot solar wind, on the other side, cooler interstellar material. The two environments were distinct, separated, maintaining their individual character right up to the boundary itself. The Sun was keeping its own atmosphere separate from the galaxy's atmosphere, and it was doing so with remarkable efficiency. Voyager 2's magnetometer readings at the crossing moment provided a piece of information that had been missing from Voyager 1's crossing 6 years earlier. Because Voyager 1 and Voyager 2 crossed the heliopause in different directions relative to the Sun, the two crossings effectively sampled the heliopause at two different points on its surface. The magnetic field direction at Voyager 2's crossing location was different from the direction at Voyager 1's crossing location, which was expected given the different geometry. But both crossings showed a consistent relationship between the magnetic field direction and the overall orientation of the outer heliosphere. The interstellar magnetic field outside the heliopause was tilted relative to the ecliptic plane in a way that matched previous estimates made from IBEX data and from observations of polarized starlight. The two Voyager crossings were beginning to triangulate the actual structure of the local interstellar magnetic field surrounding our solar system, providing direct in situ data points that grounded years of remote sensing inference in physical reality. The galaxy's magnetic field, the one threading through the neighbourhood of space our solar system travels through, was now a measured quantity rather than a theorized one. Step back from the specific measurements and the plasma densities and the magnetic field angles for a moment, and consider what the heliosphere actually does for life on Earth. Its primary role is not to contain the solar wind, though it does that. Its primary role is to act as a shield against the galactic cosmic ray environment beyond it. Galactic cosmic rays are ionizing radiation. They are high-energy particles accelerated to near light speed by supernova shock waves and other violent processes in the galaxy. When they hit complex molecules, they can break chemical bonds, disrupt cellular machinery, and damage DNA. On Earth's surface, the atmosphere and the planet's own magnetic field provide additional layers of protection. But the first and most extensive line of defense is the heliosphere itself, which deflects or absorbs approximately 70% of incoming galactic cosmic rays before they even enter the planetary region of the solar system. Without the heliosphere, the galactic cosmic ray flux at Earth's surface would be significantly higher. The biological implications are not fully understood, but the heliosphere's role as a radiation shield is a genuine factor in the habitability of the inner solar system. It is a structure that life on Earth has evolved within for more than 4 billion years, adapting to the radiation environment it creates. The heliosphere has not always provided consistent protection. Over the 4.6 billion year history of the solar system, the Sun has moved through different regions of the galaxy, some denser with interstellar material than others. When the solar system passes through a dense interstellar cloud, the increased external pressure compresses the heliosphere, potentially shrinking it enough that some of the inner solar system is exposed to higher galactic cosmic ray fluxes than at present. Conversely, when the solar system moves through a relatively empty region of the galaxy, the heliosphere can expand. Some researchers have proposed that periods of heliospheric compression associated with the solar system's passage through the spiral arms of the Milky Way, where star formation is most active and supernova rates are highest, may correlate with periods of increased cosmic ray exposure on Earth and potentially with episodes of climate change or even extinction events. The evidence is suggestive rather than conclusive, but the concept is physically sound. The size and protective capacity of the heliosphere depends on external conditions, and those conditions have varied enormously over geological time. The solar system is currently moving through the local interstellar cloud at approximately 70,000 km per hour in the direction of the constellation Hercules. Based on the cloud's known size and the solar system's velocity through it, our solar system is expected to exit the local interstellar cloud in approximately 10,000 to 20,000 years. What waits on the other side is known as the local bubble, a large region of extremely hot, extremely tenuous plasma that fills much of the local galactic neighbourhood, the result of multiple supernova explosions that occurred within the last few million years and blasted a cavity several hundred light-years across in the interstellar medium. When our solar system eventually exits the local interstellar cloud and enters the hot, thin plasma of the local bubble's interior, the pressure conditions outside the heliosphere will change dramatically. The density of the material pressing against the heliopause from outside will drop, and the heliosphere will respond by expanding. The heliopause may shift outward by tens of astronomical units, substantially increasing the shielded volume around the solar system. This transition has happened before and will happen again as the solar system orbits the galaxy, passing through environments of varying density over timescales of millions of years. Understanding the heliopause forces a reconsideration of what it would mean to travel to another star. The heliopause is not the end of the solar system in the orbital sense. The Oort cloud, the vast spherical shell of icy bodies that surrounds the solar system at distances of 10,000 to 100,000 astronomical units, extends far beyond the heliopause into interstellar space. In one sense, the Sun's gravitational influence extends to the outer edge of the Oort cloud, which is nearly 2 light years from the Sun, almost halfway to the nearest star. The heliopause is the boundary of the Sun's direct physical influence, its wind, its magnetic field, its plasma. The Oort cloud is the boundary of its gravitational influence. These are very different things. A spacecraft travelling to another star would cross the heliopause at roughly 20 astronomical units, still deep inside the solar system gravitationally. It would not exit the Sun's gravitational sphere of influence until it had travelled tens of thousands of additional astronomical units. The journey to interstellar space, in the sense of leaving the Sun's gravity well, is a completely different proposition from the journey to the heliopause, and it would take Voyager 1, at its current speed, approximately 30,000 years to complete. The Oort cloud is the most distant component of the solar system. It is a vast spherical reservoir of comets and icy bodies surrounding the solar system at distances of roughly 2,000 to 100,000 astronomical units from the Sun. The inner Oort cloud, called the Hills cloud, is denser and more disk-like. The outer Oort cloud is a thin spherical shell extending almost to the halfway point between the Sun and the nearest star. The bodies in the Oort cloud have never been observed directly, because at those distances they are far too small and faint to detect with existing telescopes. Their existence is inferred from the long-period comets that occasionally fall into the inner solar system. When gravitational perturbations from passing stars or the gravitational tide of the Milky Way galaxy itself nudge an Oort cloud body out of its stable orbit, it falls inward on a trajectory that takes thousands of years to complete, eventually swinging around the Sun as a comet visible from Earth for the first time since the solar system formed. The Oort cloud is the source of all long-period comets. It is also the outermost extent of the solar system, the final boundary before the darkness between stars. Voyager 1 is still transmitting. As of 2026, it is the most distant human-made object from Earth, at a distance of approximately 13 astronomical units from the Sun. It is moving at roughly 17 kilometers per second, which is approximately 3.6 astronomical units per year. The spacecraft is powered by 3 radioisotope thermoelectric generators, which convert the heat released by the radioactive decay of plutonium-238 into electricity. When Voyager 1 launched in 1977, these generators were producing approximately 470 watts of electrical power. Radioactive decay is not fast, but it is relentless. Plutonium-238 has 87.7 years, meaning that every 87.7 years the decay rate and the power output drop by half. By 2026, the generators are producing approximately 250 to 260 watts, down from the original 470 watts, and the power will continue to decline by roughly 4 watts per year. mission controllers have been making difficult decisions about which instruments to shut down to conserve power for the instruments still capable of returning scientifically valuable data from interstellar space. Some of the instruments that made the historic heliopause measurements have already been turned off permanently to keep the most critical ones alive. Even with reduced power and instruments operating at the edge of their remaining capability, Voyager 1 is still sending back scientifically valuable data from interstellar space. The magnetic field magnetometer is still operating and still measuring the interstellar magnetic field. The cosmic ray subsystem is still counting energetic particles, providing a continuous record of the galactic cosmic ray environment at a steadily increasing distance from the heliopause. The plasma wave science instrument still detects plasma oscillations when solar events drive waves outward to Voyager 1's location. Each measurement is unique. Every data point Voyager 1 returns is the first direct measurement of the interstellar medium at that specific location in space. No other mission is in interstellar space. No other instrument is returning data from beyond the heliopause. The information coming back from Voyager 1, at the rate of a few hundred bits per second, transmitted on a 22.4 watt radio signal across more than 22 light hours of space intercepted by the 70-meter dishes of NASA's Deep Space Network, is genuinely irreplaceable. There is no other way to get it. You cannot model it sufficiently precisely. You cannot infer it from Earth-based observations. You have to be there. Voyager 2 is also still operating in interstellar space, though at a somewhat shorter distance than Voyager 1 because its trajectory carried it in a different direction. Voyager 2 travelled southward out of the ecliptic plane, while Voyager 1 travelled northward. The two spacecraft are therefore sampling interstellar space in two completely different directions relative to the heliosphere, at two different points on the heliopause's surface. This dual sampling is enormously valuable. By comparing simultaneous measurements from two different locations in the local interstellar medium, scientists can begin to determine whether variations they observe are due to changes over time, such as fluctuations in solar activity propagating outward and affecting local conditions, or spatial variations in the interstellar medium itself at different positions. The simultaneous operation of two probes in interstellar space, both still transmitting after nearly 49 years of operation, is something that will not be repeated soon. No follow-on mission designed specifically for interstellar science has been built. Planning for an interstellar probe concept mission has been discussed at NASA, and the scientific community has repeatedly recommended it, but no funded mission exists as of 20-piece. The Voyager mission will end. The power output from the radioisotope thermoelectric generators will eventually drop below the threshold needed to operate any scientific instruments at all. Current projections suggest that Voyager 1 will no longer be able to operate any of its science instruments somewhere around 2025 to 2030, though the specific timing depends on how power is managed and which instruments are shut down in what sequence. The engineering team at JPL has been extraordinarily resourceful in extending the mission, identifying small amounts of conservable power in heater circuits and other non-critical systems that can be redirected to keep instruments alive for additional months or years beyond what initial calculations suggested was possible. But the endpoint is not in doubt. The decay of plutonium is irreversible and ongoing. At some point in the late 20s, Voyager 1 will fall silent. The last signal will arrive at the Deep Space Network antennas after its 22-hour journey. Mission controllers will send one final response, and then, after 50-plus years of continuous operation, the most successful spacecraft ever launched will transmit nothing more. It will continue travelling outward, silent, powered by nothing, in the direction of the star AC plus 79th Ear 888. which it will approach within the same general stellar neighbourhood in approximately 40,000 years. The scientific value of the Voyager measurements has inspired proposals for a dedicated interstellar probe mission that would follow Voyager's path, but with modern instruments, greater power reserves and a faster velocity that could reach the heliopause in a decade rather than 4 decades. The most developed concept, studied by a team led by Muhnut at the Johns Hopkins Applied Physics Laboratory, envisions a spacecraft launched with a solar gravity assist, falling towards the Sun to gain speed, and then using a large rocket burn at closest approach to sling itself out of the solar system at approximately 15 to 20 astronomical units per year. At that speed, the spacecraft would reach the heliopause in roughly 15 years. The science case is compelling. Voyager's instruments, designed in the late 1970s and early 1970s, were not optimized for interstellar science. A modern spacecraft with updated magnetometers, plasma analyzers, energetic particle detectors and dust analyzers would return data of far greater precision and resolution. It would reach the heliopause with full power and full instrument capability, unlike Voyager, which arrived with aging, power-depleted systems. The Heliophysics Decadal Survey of 2024 rated an interstellar probe as a priority mission. The cost and complexity remain the barriers. The heliosphere does not exist in isolation. Every star with a stellar wind creates its own equivalent of the heliosphere, a bubble of stellar wind plasma pressing outward against the surrounding interstellar medium. These stellar equivalents of the heliosphere are called astrospheres. Observations of nearby stars in ultraviolet light have revealed the neutral hydrogen walls at the boundaries of some of these astrospheres, bow shocks piling up hydrogen at the nose of the bubble, where the stellar wind meets the interstellar medium head-on. The properties of a star's astrosphere depend on the stellar wind strength, which varies enormously between different types of stars, and on the properties of the local interstellar medium through which the star is moving. For stars with strong stellar winds, the astrosphere is large. For stars that have been ejected from their birth clusters and are moving rapidly through the galaxy, the astrosphere can be dramatically compressed, with a small, tightly confined bubble swept back by the ram pressure of the interstellar medium. The Sun sits comfortably between these extremes. Its heliosphere is not the largest known, but it is large enough to provide substantial shielding, and the local interstellar cloud it is embedded in is not dramatically different from the average interstellar environment. Both Voyager spacecraft carry a gold-plated copper disc. The Voyager Golden Record contains 115 images, greetings in 55 languages, samples of music from 27 cultures and 12 minutes of sounds from Earth. It was assembled under the direction of Carl Sagan and a committee that included Ann Druyan, who would later become Sagan's wife. The record was designed as a message in a bottle, a physical artifact that could survive the journey through interstellar space and potentially be found by any civilization that encountered either spacecraft millions of years from now. The probability that any civilization will ever intercept the Voyager spacecraft is essentially zero, a fact that the creators of the record acknowledged openly. The heliosphere through which the spacecraft travelled would have shielded it partially from cosmic ray degradation while it was inside. Now, in interstellar space, the gold disk is exposed to the full galactic cosmic ray flux. Over millions of years, cosmic rays will gradually degrade the surface of the record, though the disk is expected to remain physically intact and partially readable for an extraordinarily long time. The gold plating was chosen precisely because gold is among the most chemically stable metals, immune to oxidation, resistant to corrosion. The information on that disk will outlast the civilization that made it by many orders of magnitude. The direct measurement of the heliopause has changed the way scientists think about all stellar systems. Before 2012, the structure and properties of the heliopause were primarily theoretical. Models disagreed significantly on the thickness of the heliopause transition layer, the sharpness of the plasma density jump, the behavior of the magnetic field at the boundary, and the nature of the mixing between solar and interstellar plasma. The Voyager 1 and Voyager 2 crossings provided the first direct, in situ calibration points for these models. The measurements showed that some model predictions were good: the sharp boundary nature of the heliopause, the anomalous cosmic ray drop-off, but others were wrong: the timing and behavior of the magnetic field transition, the structure of the heliosheath. Each correction to the models of our own heliosphere improves the models applied to other stellar systems. Since the Sun is the only star whose astrosphere we can directly sample, it serves as the universal calibration point for all stellar wind and astrosphere physics. Every number measured by Voyager's instruments as it crossed the heliopause echoes outward through the astrophysics literature, tightening constraints on the models that describe every star in the galaxy. Pull back now and place the heliosphere in its galactic context. The heliosphere is approximately 120 to 240 astronomical units across, depending on which direction you measure. In kilometers, that is roughly 18 to 36 billion kilometers across. The Milky Way galaxy is approximately 100,000 light-years across. 1 light-year is approximately 9.5 trillion kilometers. The heliosphere is roughly 300 billion kilometers across in its longest dimension. The ratio of the heliosphere's diameter to the galaxy's diameter is approximately 1/3 millionth. The heliosphere, the enormous bubble that protects the entire solar system, is a structure so small relative to the galaxy that contains it that it would be essentially invisible if you could see both objects simultaneously. All of human history, all of Earth's biosphere, all of the planets and moons and asteroids and comets, all of it exists inside a bubble that is, by galactic standards, a microscopic speck, a vanishingly small irregularity in the interstellar medium that the galaxy barely notices as the solar system passes through it. There is a human dimension to this story that is easy to lose inside the numbers. For the entire 4.5 billion year history of the solar system, the heliosphere has been the outer envelope of everything that exists here. It formed when the Sun formed, when the solar wind first began to blow outward, creating the bubble that would eventually surround the entire planetary system. Every organism that has ever lived on Earth, every bacterium, every dinosaur, every human civilization has existed inside this structure without knowing it was there. It is not visible from Earth. It is not something that anyone ever saw or felt or suspected until the 20th century brought the science to identify it. Eugene Parker's 1958 paper was the first time anyone proposed a mechanism for this boundary. The theoretical work that followed built up a picture over decades, and then, in 2012 and 2018, 2 spacecraft that humanity had launched 35 years earlier provided the direct measurements. We found the edge of our cosmic home. We built machines that crossed it, and what we found there told us not just about the boundary itself, but about the structure and identity of the entire neighborhood of the galaxy we inhabit. There is something almost poetic about how the definitive confirmation of Voyager 1's heliopause crossing arrived. It came through sound. Not sound in the literal sense, because sound cannot travel through the near vacuum of interstellar space. But plasma oscillations detected by Don Gurnett's plasma wave science instrument have acoustic analogues. The instrument detects oscillations in the electron density of the surrounding plasma at frequencies that, when converted to the audio frequency range for human listening, produce a tone. Scientists have released audio files derived from Voyager 1's plasma wave measurements at the moment of the heliopause crossing, and from the solar events that cause plasma oscillations in interstellar space beyond the boundary. The tone shifts audibly as the spacecraft crosses the boundary, rising in pitch to reflect the higher plasma density of the interstellar medium. There is something in the idea that we confirmed our entry into interstellar space through a frequency, a resonance of the plasma surrounding a machine travelling at 17 kilometers per second in the dark between the stars, detected by a 45-year-old instrument smaller than a briefcase, transmitted on a signal 22 light hours long, and decoded by scientists sitting at computers in Pasadena, California. The heliosphere is not static. The Sun's activity varies on an approximately 11-year cycle, alternating between periods of high activity called solar maximum, when sunspot activity, solar flares, and coronal mass ejections are most frequent, and periods of lower activity called solar minimum. During solar maximum, the solar wind carries more energy and more mass outward per unit time, pressurizing the heliosphere from the inside and pushing the heliopause outward. During solar minimum, the solar wind weakens, the internal pressure of the heliosphere drops, and the heliopause moves slightly inward. These variations are not enormous in absolute terms. The heliopause probably moves by no more than a few astronomical units over the course of an 11-year solar cycle. But they are real, measurable effects that Voyager's instruments can detect. A solar maximum that occurred roughly a decade before Voyager 1's 2012 heliopause crossing had sent a wave of enhanced solar wind pressure propagating outward through the heliosphere, and this pressure wave may have contributed to the sharpness of the boundary transition that Voyager 1 observed. The boundary is alive. It breathes with the Sun. Consider what the heliosphere would look like if the Sun were a different type of star. The stellar wind strength varies enormously across the range of stars in the Milky Way. A massive, hot, blue-white star generates a stellar wind that is millions of times more powerful than the solar wind. Its equivalent of the heliosphere would be vast beyond comparison, an enormous magnetosphere extending for hundreds or thousands of astronomical units in every direction. At the other extreme, cool, dim red dwarf stars, which are the most common type of star in the galaxy, generally have weaker stellar winds than the Sun, and their astrospheres are correspondingly smaller and less protective. Some models suggest that red dwarf astrospheres may be too small and weak to provide significant shielding against galactic cosmic rays for planets orbiting within the habitable zone, which for a red dwarf lies very close to the star. If this is correct, it would mean that the habitable zones of the most common stars in the galaxy are exposed to galactic cosmic ray fluxes far higher than what Earth experiences inside the Sun's heliosphere. This would be relevant to the habitability of such planets in ways that are not yet fully understood. Return now to the termination shock and the mystery of the anomalous cosmic rays. When Voyager 1 crossed the termination shock in December 2004, one of the expected signatures of that crossing was a peak in anomalous cosmic ray intensity. Theory predicted that the termination shock was the primary site where interstellar neutral atoms, swept into the heliosphere and ionized, would be accelerated by the energy available in the solar wind's deceleration. The expected signature was not found. The anomalous cosmic rays did not peak at the termination shock. They were abundant in the heliosheath, but their peak appeared to be somewhere else, somewhere that Voyager 1 could not identify cleanly. When Voyager 2 also crossed the termination shock in 2007 and made the same observation, the scientific community began to seriously consider that the termination shock was not the primary acceleration site for anomalous cosmic rays. Subsequent analysis pointed toward the heliosheath itself, and specifically toward the region where the solar wind flow is compressed and diverted around the nose of the heliopause, as a likely major acceleration site. The stagnation region in front of the heliopause, where the solar wind slows nearly to a halt before being deflected sideways, may be the most energetically active part of the outer heliosphere. The stagnation region is a zone in the very outermost part of the heliosheath, just inside the heliopause on the sunward side, where the solar wind plasma essentially stops moving outward and begins to flow sideways along the heliopause surface. Think of it as the bow of a ship, where water piles up and flows around rather than continuing forward. In the heliosphere, this is the region where solar plasma piles up against the heliopause boundary before deflecting around it. The plasma in this region is under the highest pressure, the most compressed, and the most energetically dense of any location in the outer heliosphere. When Voyager 1 was travelling through this region in the year or two before its heliopause crossing, it observed some of the most variable and anomalous particle measurements of its entire journey. The magnetic field was fluctuating. The particle populations were behaving in ways that shifted rapidly on timescales of days. This was the most active region of the outer heliosphere, the frontier where the Sun's domain was directly confronting the interstellar medium, where the two environments were pressing against each other across the thinnest possible interface. The heliopause is not merely a boundary in pressure and plasma density, it is a magnetic wall. On the solar side, the magnetic field is the Parker spiral, wound by the Sun's rotation into a vast pinwheel of field lines that fill the entire heliosphere. On the interstellar side, the magnetic field has a completely different structure, threading through the interstellar medium in a direction determined by the local galactic magnetic field, which runs at a roughly 30 to 40 degree angle to the ecliptic plane. The transition between these two magnetic field regimes happens at the heliopause, in a thin layer where field lines from two completely different origins meet and reconnect. Magnetic reconnection is a process where field lines with opposing orientations break and reconnect in a new configuration, releasing energy in the process. The heliopause is a site of continuous magnetic reconnection, where solar field lines and interstellar field lines are constantly interacting at the boundary. This reconnection has two effects. It allows some interstellar particles to enter the heliosphere along reconnected field lines, even while the overall boundary remains intact. And it provides a mechanism for mixing at the boundary that is distinct from the pressure gradient mixing that would occur in its absence. The heliopause is an active interface, not a passive wall. The magnetic reconnection happening at the heliopause has physical consequences that extend back into the heliosphere. When an interstellar magnetic field line reconnects with the solar field line, the resulting merged field line has one end anchored in the outer heliosphere and the other end threading into the interstellar medium. Particles moving along that merged field line can travel from the interstellar medium into the heliosphere without physically crossing the pressure boundary. This is believed to be one of the mechanisms by which some galactic cosmic rays penetrate the heliosphere at the heliopause. They do not punch through the boundary, they slip through along reconnected field lines. The efficiency of this process depends on the local geometry of the magnetic field at the point of reconnection, which changes continuously as the solar wind variations propagate outward and as the solar system moves through slightly different regions of the interstellar medium. The leakage of galactic cosmic rays through the heliopause via magnetic reconnection is one reason that the shielding efficiency of the heliosphere is not 100%. The heliosphere blocks most galactic cosmic rays, but it cannot block them all, because the magnetic field at the boundary is not a uniform impenetrable wall. It is a dynamic, ever-changing interface that allows some of the galaxy's most energetic particles to slip through. To understand what the heliosphere's cosmic ray shielding means practically, consider the numbers. The galactic cosmic ray flux outside the heliosphere, in the interstellar medium, is approximately 1,000 to 2,000 particles per the square centimetre per second when integrated over all energies. These particles span an enormous range of energies, from a few 100 million electron volts to many quadrillions of electron volts for the most extreme. The heliosphere reduces this flux significantly for particles in the lower energy range. For galactic cosmic rays with energies below about 1 billion electron volts, the heliosphere provides the most effective shielding, blocking, or deflecting the majority. For particles with energies above about 10 billion electron volts, the heliosphere's shielding is minimal. The highest energy galactic cosmic rays pass through the heliosphere as if it were barely there. At Earth's orbit, the solar wind modulation reduces the measured flux by approximately a factor of 2 to 4 compared to what it would be in interstellar space. During solar maximum, when the heliosphere is most inflated and its internal magnetic field is most turbulent, the modulation is strongest. During solar minimum, it weakens. The practical consequence of the heliosphere's finite cosmic ray shielding matters directly for any future human travel beyond the inner solar system. Astronauts on the International Space Station, which orbits within Earth's magnetic field, receive radiation doses roughly 10 times higher than people on the surface, but still within an acceptable range for long-duration missions. Astronauts travelling to the Moon or Mars would leave Earth's magnetic field and be exposed to both the solar wind particle environment and the attenuated galactic cosmic ray flux that the heliosphere allows through. Beyond Mars, as a spacecraft travels into the outer solar system and approaches the heliopause, the galactic cosmic ray flux continues to rise as the heliosphere's modulation effect weakens with increasing distance from the Sun. Any crewed mission to the outer solar system would face radiation doses that current shielding technology cannot adequately mitigate over multi-year mission durations, and any mission that crossed the heliopause into interstellar space would expose its crew to the full, unmodulated galactic cosmic ray environment. The heliopause is not just a scientific boundary. For any future humans travelling beyond it, it is the point where the Sun stops protecting you and the galaxy begins. The heliosphere's role as a radiation shield has direct implications for thinking about life elsewhere in the universe. The galactic cosmic ray environment outside stellar astrospheres is energetic enough to cause significant DNA damage in exposed organisms over time. Life on Earth evolved in an environment where the heliosphere was providing partial protection. Whether life could evolve or persist in an environment with significantly higher cosmic ray flux is not known. Some extremophile organisms on Earth can tolerate radiation levels orders of magnitude higher than the background on Earth's surface, which suggests that radiation tolerance is achievable through evolution. But the sustained continuous bombardment of galactic cosmic rays at the full interstellar flux would be a very different environment from any that Earth life has experienced inside the heliosphere. Stars that do not generate stellar winds, or stars whose stellar winds are too weak to create a significant astrosphere, would expose any orbiting planets to the full interstellar cosmic ray environment. The heliosphere adds a layer to the habitability question. A star's ability to sustain complex life may depend not just on its luminosity and spectral type, but on the strength of its stellar wind and the size of the protective bubble it creates. The months leading up to Voyager 1's final heliopause crossing in August 2012 were marked by a series of events that in retrospect can be read as a sequence of signals that the spacecraft was entering a novel region. In May 2012, scientists noticed that the intensity of low-energy ions originating from inside the heliosphere had dropped by half compared to the previous month. These ions were solar in origin, and their sudden reduction suggested that Voyager 1 was entering a region where solar wind particles were dramatically depleted. Simultaneously, the intensity of galactic cosmic rays increased by 9% in a single day. Taken together, these two changes were exactly what would be expected at the heliopause. and some scientists at that point believed the spacecraft had already crossed it. But the magnetic field direction did not change. The field remained in the orientation characteristic of the heliosphere's interior. Scientists were confronted with a puzzle. How could the particle environment be so clearly interstellar while the magnetic field was still solar? The answer was the discovery of a region unlike anything that had been predicted, which the Voyager team initially described as a magnetic highway. The magnetic highway was the name given to the region Voyager 1 entered in mid-2012 before its final heliopause crossing. In this region, the particle population had the characteristics of interstellar space, depleted of solar wind ions and enriched in galactic cosmic rays, but the magnetic field direction still aligned with the heliospheric field rather than the interstellar field. The explanation that emerged was that Voyager 1 had entered a region where the magnetic field lines of the heliosphere were connected to the magnetic field lines of the interstellar medium through a series of reconnection events that effectively opened pathways for particles to travel between the two environments, while the overall field orientation was still transitioning. Solar wind particles could escape outward along these connected field lines, and galactic cosmic ray particles could stream inward, all while the bulk magnetic field direction remained roughly heliospheric. It was as if the frontier between the two environments was becoming porous in particle terms before it fully transitioned in magnetic terms. The magnetic highway was a previously unknown type of boundary region, unique to the interface between a stellar wind and the interstellar medium, and it was discovered entirely because Voyager 1 happened to pass through it while still carrying functioning particle and magnetic field instruments. August 25, 2012, write it down. The date belongs alongside July 20th in 69 and April 12th in 61 in the record of the moments when humanity crossed a threshold it had never crossed before. On July 20th in 69, a human being stood on the surface of another world for the first time. On April 12th in 61, a human being left Earth's atmosphere for the first time. On August 25th, 2012, an object built by human hands crossed out of the solar system for the first time. No human was aboard Voyager 1. The crossing was made by a machine launched 35 years earlier by engineers and scientists who calculated trajectories and built instruments and connected circuit boards in clean rooms in Pasadena, and then handed their creation over to physics and waited. But the knowledge that came back from that crossing, the magnetic field data, the particle measurements, the plasma oscillations, that knowledge is human knowledge. Voyager is an extension of human curiosity, a physical projection of the same drive that built the first boats and mapped the first coastlines and climbed the first mountain passes to see what was on the other side. August 25th of 2012 is the date that Drive crossed the edge of the solar system. The confirmation of Voyager 1's heliopause crossing did not arrive as a single dramatic moment. The data had been accumulating since August 25th, 2012, and the formal scientific analysis took months. The plasma oscillation measurement that provided the definitive proof came from data collected in April and October 2013, and was published in the journal Science in September 2013. Ed Stone, who had been Voyager's project scientist since 1972, gave the press conference. He'd been on the mission for 41 years at that point. He'd been involved in the interpretation of Voyager data since before the spacecraft launched. He'd watched Jupiter's volcanic moons come into focus, and Saturn's rings reveal their structure, and the outer planets become real places, rather than distant points of light. And now he was standing at a lectern confirming that the mission he had devoted 4 decades of his career to had become the first human artifact to enter interstellar space. The emotional content of the moment, which Stone expressed with characteristic scientific restraint, was enormous, but the data was what mattered. The plasma oscillation frequency was 2.6 kHz. That frequency corresponded to an electron density of 0.08 per cubic centimetre. Interstellar space. Confirmed. Despite the Voyager crossings and the IBX mapping and decades of theoretical modelling, there are fundamental aspects of the heliosphere's structure that remain unknown or debated. One of the most basic questions is the shape of the heliosphere's tail. For decades, the consensus picture was a comet-like shape with a long, extended heliotail trailing behind the solar system's direction of motion. More recent analysis of IBEX data, published in 2016 by a team led by Mehraf O.H. Fair, suggested that the heliotail might be dramatically different from the comet picture. The new model, called the Poisson model for the two lobes its tail forms, suggested that the interstellar magnetic field pressure is strong enough to confine the heliotail and prevent it from extending far in the traditional comet-like manner. Instead of a long, flowing tail, the heliosphere might have two pinched lobes, above and below the plane of the ecliptic, where the heliotail material is constrained by the interstellar magnetic field. The debate between the comet model and the croissant model continues in the scientific literature. Both are consistent with some aspects of the available data. Resolving it definitively would require either a dedicated interstellar probe mission or better remote sensing measurements of the heliosphere's boundaries. Beyond the heliopause, there is a structure called the hydrogen wall. The hydrogen wall forms in the interstellar medium just outside the heliopause on the leading side of the heliosphere, where neutral hydrogen atoms in the interstellar medium pile up as they are deflected by the heliosphere's outer boundary. Neutral hydrogen cannot penetrate the heliopause easily because of charge exchange interactions with the solar wind plasma just inside it, so it slows down and accumulates in a compressed region just outside the heliopause, creating a wall of enhanced hydrogen density. This hydrogen wall was detected by NASA's Hubble Space Telescope in 1996 through its absorption effect on the ultraviolet light from nearby stars. When Hubble looked at the Sun in Lyman alpha ultraviolet light, the absorption pattern showed an excess component that matched the spectral signature expected from a region of warm, slightly decelerated hydrogen at the location of the hydrogen wall. The same signature was later found around other nearby stars, confirming that the hydrogen wall is a universal feature of stellar astrospheres. It marks the very first transition in the sequence of boundaries that separates the interior of a stellar system from open interstellar space. The Hubble Space Telescope's detection of the hydrogen wall opened a new way to study the heliosphere, not from the inside with in situ spacecraft measurements, but from the outside by looking at how the structure affects the ultraviolet light from nearby stars. When Hubble observes a nearby star in Lyman alpha ultraviolet, the light from that star passes through the interstellar medium, through the hydrogen wall of the solar heliosphere, and then through the inner heliosphere before reaching the telescope. Each component leaves a characteristic absorption signature in the spectral profile of the light. By modelling these signatures and subtracting them from observed spectra, astronomers can infer properties of the hydrogen wall and the inner heliosphere even without sending a probe there. This technique has been used to estimate the properties of astrospheres around more than a dozen nearby stars. Some of these stars show larger hydrogen wall signatures than the Sun, suggesting stronger stellar winds and larger astrospheres. Others show no detectable hydrogen wall signature, which may indicate very weak stellar winds or stellar wind properties that do not produce a significant hydrogen pileup at the astrosphere boundary. The Sun's astrosphere is, by this measure, roughly average in size for a star of its type. What would interstellar space feel like in a physical sense if you were there? Not subjectively, since outside a spacecraft there is no atmosphere, no temperature in the ordinary sense, and no one to experience anything. But in terms of what a sensitive instrument would detect, the most noticeable change crossing the heliopause would be the particle environment. Inside the heliosphere, you are bathed in the solar wind, a continuous stream of electrons and protons flowing outward at hundreds of kilometers per second. This stream is not energetic enough to harm a well-shielded spacecraft, but it is unmistakably present in the data. Crossing the heliopause, the solar wind drops away and the galactic cosmic ray environment takes over. The particles bombarding a spacecraft in interstellar space are not the gentle, relatively slow solar wind particles. They are cosmic rays, some of the most energetic particles in the universe, moving at near light speed, carrying energies billions of times higher than the particles in the solar wind. The flux, the number of particles per second per unit area, is lower than in the solar wind, but the energy per particle is vastly higher. Interstellar space in particle terms is quieter but more energetically extreme. The material Voyager 1 is currently moving through, the local interstellar cloud, has been characterized with reasonable precision. Its temperature is approximately 6,000 to 700 Kelvin, warm enough that much of its hydrogen is ionized, though a significant fraction remains neutral. Its density is approximately 0.3 hydrogen atoms per cubic centimeter, give or take a factor of 2. Its bulk flow relative to the solar system is approximately 23 to 25 kilometers per second, moving in the direction that corresponds, from Earth's perspective, to roughly the direction of the star Vega in the constellation Lyra. The magnetic field threading through the local interstellar cloud has a strength of approximately 2.5 micro-Gauss, a tiny field by human standards but meaningful in terms of its ability to direct and channel charged particles. The composition of the local interstellar cloud matches the rough cosmic average of hydrogen and helium with trace amounts of heavier elements. It is not a chemically unusual environment. It is, by the standards of the galaxy, fairly ordinary gas, warm and thin, and laced with a weak magnetic field. The heliosphere exists as a pressurized bubble within this ordinary interstellar material, no more exotic in its local galactic context than a soap bubble floating in fog. Let us try to hold the scale one more time. The Sun is one of approximately 200 to 400 billion stars in the Milky Way galaxy. Its heliosphere, its sphere of direct physical influence, extends roughly 20 astronomical units in the direction the solar system is moving. In that direction, it is approximately 18 billion kilometers in radius. The nearest star, Proxima Centauri, is approximately 4.24 light-years away, which is approximately 40 trillion kilometers. The radius of the heliosphere is 18 billion kilometers. The distance to the nearest star is 40 trillion kilometers. The ratio is roughly 1 to 200. The heliosphere's radius is approximately 1/2000th of the distance to the nearest star. Now consider that the Milky Way is approximately 100,000 light-years across, about 24,000 times larger than the distance to Proxima Centauri. A single heliosphere, the entire volume that the Sun physically dominates, is so small relative to the galaxy that if you scaled the Milky Way down to the size of North America, the heliosphere would be smaller than a bacterium. One bacterium-sized bubble. That is the Sun's domain. That is the entire arena of 4 billion years of planetary history and all the life that has ever lived. Voyager 1 is currently transmitting at a power of 22.4 watts. The signal spreads outward in all directions as it travels, diminishing in strength with the square of the distance. By the time it reaches Earth's deep space network antennas, the signal power is extraordinarily small, 100 billion times smaller than a billionth of a watt. The 70-meter diameter DSN antennas are barely large enough to collect enough signal photons to decode the data. The data rate from Voyager 1 is now approximately 60 bits per second for science data, 16 bytes of information per second from a machine 22 light hours away. In the late 2020s, the power output will drop below the threshold needed to run the instruments. The team at JPL will continue to track the spacecraft's carrier signal, the raw radio wave without any data modulated onto it, as long as the transmitter produces any detectable output. At some point, the carrier itself will fade below detection. The last signal will arrive at Earth approximately 22 hours after the transmitter dies, and then the most distant object ever built by human hands will continue its journey in silence, outward at 17 kilometers per second for the rest of time. The heliopause crossing of Voyager 1 is one of the genuinely rare events in the history of human exploration that carries both scientific and existential significance simultaneously. Scientifically, the measurements returned from the crossing and from the years since are unique, irreplaceable calibration quality data about the interface between the solar system and the interstellar medium that cannot be obtained any other way. Existentially, the crossing represents the first time a human artifact has physically left the sphere of the sun's direct influence. This is not a metaphor, it is a physically precise description. Before August 25, 2012, everything that had ever been launched by humanity was either still inside the heliosphere, or destroyed or in orbit around Earth or the Moon. After August 25, 2012, one of those objects was in interstellar space. The conceptual difference is profound. There is a boundary, we crossed it. It happened in our lifetimes, or at least in the lifetimes of people now alive. The transition from a species entirely confined to the interior of its star's sphere of influence to a species that has placed one of its creations beyond that boundary is a transition that, viewed from the long perspective of cosmic time, has happened essentially instantaneously. From Voyager 1's current location in interstellar space, approximately 63 astronomical units from the Sun, our star is still the brightest object in the local sky, but it is dramatically diminished from the object we know. The Sun at 163 astronomical units would appear as a star of approximately -3 magnitude, still distinctly the brightest star in the sky from that distance, but no larger to the naked eye than Venus appears from Earth. No disk, no corona, no prominences, just a very bright point of light, significantly brighter than any other star, but a point nonetheless. The solar system planets would be invisible without optical aid. Earth itself would be completely undetectable without a telescope. The Sun's light falling on the surface of Voyager's golden record is now 163 squared, or roughly 26,000 times weaker than it was at Earth's distance from the Sun. The gold disk is cold. The spacecraft is cold, and yet it transmits. An antenna pointing back toward a bright star in the direction of the constellation Ophiuchus sends its signal home at the speed of light, and 22 hours later, someone in Pasadena reads what it says. Voyager 1 is travelling in the direction of the constellation Ophiuchus. In approximately 40,000 years, it will pass within approximately 1.6 light-years of the star AC, plus 79, 38, 88, a dim red dwarf in the constellation Q, MELO, Par, De, Lis. This is not a close pass in any meaningful sense. The gravitational influence of that star will barely be felt by Voyager at that distance. It will not be captured, not deflected significantly. It will simply pass through the outer gravitational reach of another star's domain and continue onward. Voyager 1 will continue travelling through the galaxy, essentially forever, since there is nothing in its path to stop it and no mechanism in interstellar space that will decelerate it significantly. In 5 billion years, when the Sun expands into a red giant and eventually consumes the inner planets including Earth, Voyager 1 will be approximately 85,000 light-years from its origin, roughly the diameter of the Milky Way itself away from where it was built. The golden record will still be there, still sealed against the cold of interstellar space, carrying its cargo of music and images and greetings from a civilization that will be unrecognizably ancient by then if it exists at all. The heliopause, when you hold all of this knowledge together, is a structure of extraordinary philosophical significance. It is not just a boundary in pressure or density. It is the outermost reach of the Sun's direct physical authority over the space surrounding it. It marks where the Sun's wind stops, where its magnetic field yields to the galaxies, where its particles give way to the interstellar medium. Everything inside the heliopause is, in a deep physical sense, part of the Sun's domain. The Sun formed this region from the gas of the primordial solar nebula more than 4 billion years ago. It has been maintaining it ever since, inflating it with its constant wind, threading it with its magnetic field, shielding it from the galaxy's most energetic radiation. Every planet, every moon, every ocean, every living cell, every thought that has ever been thought on Earth has happened inside this domain. The heliopause is the edge of that domain. It is the outermost limit of the Sun's reach, and everything you have ever known is on the other side of it, small and protected inside the Sun's ancient, persistent bubble. The knowledge that came back from Voyager's crossings did not come quickly. The spacecraft launched in 1977. The termination shock crossing came in 2004, 27 years later. The heliopause crossing came in 2012, 30 years after launch. The plasma oscillation confirmation came in 2013, 36 years after launch. The paper that described the heliopause crossing in full detail was published in the journal Science in September 2010. The scientists who built the instruments on Voyager 1 had designed those instruments in the late 1960s and early 1970s. The engineers who calibrated the magnetometer and the cosmic ray detectors and the plasma wave instrument had, by the time the heliopause was crossed, mostly retired. Some had died. The people who received the signal that confirmed the crossing were in many cases decades younger than the people who built the instrument that generated the signal. Scientific knowledge accumulates this way, across careers, across lifetimes. The investment of a career's worth of effort bears fruit not when the scientist is young and brilliant and building the instrument, but 35 years later, when the spacecraft finally reaches the edge of the solar system and reports back. None of the Voyager data would exist without the Deep Space Network, NASA's global system of large radio antennas that maintains communication with spacecraft throughout the solar system and beyond. The Deep Space Network was established in 1963 and consists of 3 antenna complexes located approximately 20 degrees apart in longitude around the Earth. At Goldstone in California's Mojave Desert, near Madrid in Spain, and near Canberra in Australia. This 3-complex arrangement ensures that at least one antenna is always in line of sight to any point in deep space regardless of Earth's rotation. The 70-meter antennas, the largest in the network, are among the most sensitive radio receivers ever built. To receive Voyager 1 signal at 22 light-hours distance requires collecting the energy from a 22.4-watt transmitter spread across the entire celestial sphere, which reduces the received power to an almost immeasurably small quantity. The DSN also transmits commands to Voyager, which requires significant transmitted power to achieve a detectable signal at Voyager's distance. Maintaining communication with Voyager 1 in interstellar space is one of the most demanding operational challenges in the history of space exploration, and it has been sustained continuously for more than 48 years. Voyager 1 launched with 11 science instruments. Several were shut down long ago to conserve power. The planetary cameras, which produced the iconic images of Jupiter and Saturn and their moons, were powered off in 1990 after returning the pale blue dot photograph. The ultraviolet spectrometer was turned off in 1998. The photopolarimeter system was disabled. By 2025, 4 instruments were still operating. The magnetometer, which measures the interstellar magnetic field. The cosmic ray subsystem, which counts energetic particles across multiple energy channels. The low-energy charged particle detector, and the plasma wave science instrument. These 4 instruments represent the legacy of dozens of scientists and engineers who designed and built them in the 1970s. They are operating in an environment no one who designed them had ever directly measured. They were calibrated in Earth laboratories using theoretical estimates of what interstellar space might contain. Now they are in interstellar space, and the measurements they are returning are informing the next generation of models and the next generation of missions, all built on the foundation of what a 1970s-era spacecraft discovered when it travelled farther than anyone had gone before. Step back even further in time, and the heliosphere reveals another role, one that connects to the earliest history of the solar system. When the planets were forming more than 4 billion years ago, the solar wind was far more intense than it is today. The young sun was in a more active phase of its stellar evolution, and its wind was blowing with a power that dwarfed the current solar wind. This intense early solar wind played a role in shaping the formation of the inner planets. It would have stripped the atmospheres of any protoplanetary bodies that formed before they reached sufficient mass to retain their atmospheres gravitationally. It influenced the distribution of water in the early solar system, helping to drive volatile rich material from the inner region of the solar nebula outward to the outer solar system. The early heliosphere created by this intense wind was likely much larger than the current heliosphere, pressing the heliopause outward to distances that may have exceeded the current extent of the Oort cloud. Over the Sun's lifetime, as its activity has gradually declined with age, the heliosphere has settled to its current size. It has been evolving continuously, adapting to changes in the Sun and in the interstellar environment for 4.6 billion years. Our solar system is not travelling through a randomly uniform region of the galaxy. It is moving through a specific, well-characterized region called the local bubble, a large cavity in the interstellar medium roughly 1,000 light-years across, excavated by multiple supernova explosions over the past few million years. The interior of the local bubble is filled with hot, extremely tenuous plasma at temperatures of approximately 1 million Kelvin, vastly hotter but far less dense than the material outside it. This hot bubble material was created by the explosions of massive stars in the Scorpius-Centaurus OB association, a group of young massive stars that has been generating supernovae for the past 10 to 15 million years. Our solar system entered the local bubble approximately 5 million years ago, based on the ages of the supernova remnants and the solar system's trajectory through that region of the galaxy. Within the local bubble, our solar system currently sits inside the local interstellar cloud, one of several cool, dense cloudlets that float through the hot local bubble interior like condensation droplets in a hot gas. The heliosphere is pressing outward against the exterior pressure of this cool cloud. Beyond the cloud's edge, the even lower external pressure of the hot local bubble interior would allow the heliosphere to expand dramatically. Over the entire lifetime of the solar system, approximately 4 billion years of orbiting the Milky Way galaxy at a speed of 230 kilometers per second, the Sun has completed roughly 18 to 20 full orbits of the galactic center. Each orbit takes approximately 225 to 250 million years, a unit of time sometimes called a galactic year or cosmic year. During each galactic year, the solar system has passed through different regions of the galaxy. with different interstellar medium densities, different galactic cosmic ray fluxes, and different stellar neighborhoods. When the solar system is inside a dense interstellar cloud, the heliosphere is compressed. When it is in a hot, sparse region like the local bubble, the heliosphere expands. When the solar system passes through a galactic spiral arm, where star formation is active and supernova rates are high, the cosmic ray flux in the local region of the galaxy is temporarily elevated. Some researchers have proposed that these regular exposures to enhanced cosmic ray fluxes during spiral arm passages may have biological consequences, potentially correlating with mass extinction events whose timing roughly matches the expected period of spiral arm crossings. The evidence is circumstantial, the correlations are approximate, and the mechanisms are debated, but the concept is physically sound. The heliosphere, in its structure and properties, is not only a shield and a physical boundary, it is a record keeper. The heliospheric plasma carries within it the imprint of the Sun's historical activity, encoded in the composition and energy distribution of the particles filling it. The isotopic composition of the solar wind, for instance, which has been measured in situ by both Voyager and the Genesis mission that collected solar wind samples and returned them to Earth, carries information about the Sun's elemental composition and nuclear processes. The structure of the heliosphere at any given moment reflects the integrated history of solar wind variations over the travel time of the solar wind from the Sun to the heliopause, which is approximately 1 to several years depending on solar wind speed and distance. The heliosheath retains a scrambled record of solar wind variations over longer periods. The heliotail extends this record outward for potentially thousands of years of solar activity history. Somewhere in the vast, barely observable heliotail, the imprint of every major solar event for the past several thousand years is encoded in the plasma, stretched out and diluted but physically present, waiting for an instrument sensitive enough to read it. If a civilization existed in the Alpha Centauri system, 4.24 light-years from the Sun, with telescope technology significantly more advanced than what humanity currently possesses, what could it detect about our solar system? It could observe the Sun's light and determine its spectral type and luminosity. It could, with extreme difficulty, detect the presence of the larger planets by their gravitational effects on the Sun's motion, or by the dimming of the Sun's light during transits. But could it detect the heliosphere? Possibly. The hydrogen wall at the heliopause scatters Lyman alpha ultraviolet light in a characteristic way that has already been detected by our own Hubble Space Telescope around nearby stars. An advanced civilization capable of the equivalent observation could infer the presence of our heliosphere, its size, and the properties of its outer boundary from the absorption signature of the hydrogen wall in our Sun's ultraviolet spectrum. They would see a Sun with a heliosphere of roughly typical size for its stellar type, embedded in a warm, partially ionized interstellar cloud. They would know from this observation alone something about the radiation environment experienced by any planets orbiting within our solar system. Whether any civilization is actually making this observation is unknown. Is the heliosphere unusual? Does the Sun generate a larger or smaller, more or less protective bubble than typical for a star of its type? Observations of other astrospheres through the hydrogen wall detection technique and through models of stellar wind properties across the population of Sun-like stars suggest that the Sun's heliosphere is roughly typical. The Sun is a G-type main sequence star, and the stellar winds of G-type stars span a range of strengths, with the Sun sitting near the middle of the distribution. Some Sun-like stars appear to have much stronger stellar winds and correspondingly larger astrospheres. Others appear to have weaker winds. The Sun may actually be on the lower end of stellar wind strength for its spectral type, based on indirect measurements of magnetic activity levels in comparable stars, but the data is uncertain enough that this conclusion should be treated with caution. What seems clear is that the Sun's heliosphere, while not extreme in any direction, provides a reasonable level of cosmic ray shielding for the inner solar system. Whether life could have evolved here with a significantly smaller or weaker heliosphere, or whether it would be more abundant in a solar system with a larger, more protective one, is a question that current understanding cannot answer. There is something quietly extraordinary about the people who devoted their scientific careers to an object that was launched before most of them had finished their graduate education. Ed Stone joined the Voyager project as project scientist in 1972, 5 years before launch, and remained actively engaged with it for more than 5 decades. Don Gurnett built the plasma wave science instrument and spent decades waiting for it to detect the oscillation that would confirm the heliopause crossing. Stamatios Krimiegis led the energetic particle science team through the planetary encounters, through the long crossing of the outer heliosphere, through the termination shock, through the heliosheath, and to the boundary of interstellar space. These scientists spent major portions of their lives in service of a mission that was always, at any given moment, farther from its most important destination than it had been the day before. The Voyager mission is unique in the history of space exploration for the longevity of its scientific team. No other mission has maintained the same core group of investigators for anything approaching the same duration. The continuity of institutional knowledge about the spacecraft's behavior, its instrument calibrations, its accumulated peculiarities is part of what made the heliopause crossing interpretable at all. There is a way of thinking about the heliosphere that does not appear often in scientific literature, but that seems worth saying plainly. The heliosphere is home, not home in the sense of the Earth, the biosphere, the specific planet where life evolved, but home in the sense of the largest structure that contains and protects everything that is ours. Every planet, every body of water, every mountain, every molecule of air, every living thing that has ever existed on Earth has existed inside this bubble for the entire history of complex life. When Voyager 1 crossed the heliopause, it left home. Not in any emotional sense, since the spacecraft has no emotions, but in the most physically precise sense possible. It left the domain of the Sun's direct protection. It passed from the environment shaped and maintained by our star for billions of years, into the environment shaped by the galaxy, by supernovae long extinguished, by magnetic fields that thread through the space between stars. The boundary it crossed is real, and what lies beyond it is as different from the interior of the heliosphere as the bottom of the ocean is from the open sky above the waves. Carl Sagan once described the Earth, as seen from Voyager 1's distance of 6 billion kilometers in 90, as a mote of dust suspended in a sunbeam. From the heliopause, 18 billion kilometers farther out, even the context of that image is gone. The pale blue dot that Sagan described would be invisible without optical aid from Voyager's current location. The entire inner solar system, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, all of them, would be invisible to the naked eye from the heliopause. The Sun itself would be a bright star, unmistakably the brightest object in the local sky, but a star nonetheless. What Sagan said about the pale blue dot that every king and peasant, every moment of courage or cowardice, every creator and destroyer of civilizations, every saint and sinner in the history of the human species, lived and died on a mote of dust suspended in a sunbeam, becomes something even more vertiginous when you stand at the heliopause and realize that even that mote is invisible, swallowed into the brilliance of its parent star, lost inside a bubble so small that the galaxy does not notice it. As the solar system continues its journey through the galaxy, the interstellar environment directly ahead of it is not static. The local interstellar cloud, the material the heliosphere is currently pressing against from the inside, is itself moving and evolving over time. Based on the solar system's trajectory and the cloud's estimated structure, our solar system will exit the local interstellar cloud in approximately 10,000 to 20,000 years, though the uncertainty in this estimate is large. When it does, the external pressure on the heliopause will change. In the hot, thin interior of the local bubble, the heliosphere is expected to expand significantly. Some models suggest it could expand to 2 or 3 times its current size as the external pressure drops. This expansion would not be instantaneous. It would propagate outward at the speed of sound in the heliospheric plasma, so the heliopause would gradually move outward over decades to centuries as the new pressure equilibrium is established. The nature of the cosmic ray shielding would change as well. In the thin plasma of the local bubble's interior, the particle environment outside the heliosphere would be different from the particle environment currently outside it. What those differences mean for any living things on Earth 10,000 years from now is a question that requires more detailed modelling than currently exists. If a follow-on interstellar probe were launched today with the advanced capabilities that have been proposed, what would it find when it crossed the heliopause in approximately 15 years? It would find everything Voyager found, but with much greater clarity and precision. The plasma density jump at the heliopause, measured by Voyager as a factor of roughly 130 increase from inside to outside, would be measured across its full energy spectrum, rather than inferred from oscillation frequencies. The magnetic field transition would be mapped in full 3-dimensional detail as the spacecraft crossed through the transition layer, rather than being measured at a single point by aging magnetometers. The cosmic ray energy spectrum just outside the heliopause, which Voyager measured imprecisely because its instruments were calibrated for a different environment, would be characterized across 10 decades of energy, and the spacecraft would continue outward through interstellar space, carrying modern particle detectors and dust analyzers capable of identifying the composition of interstellar grains, the micrometer-scale solid particles that drift through the space between stars carrying the chemical legacy of generations of stellar evolution, the atoms forged in stellar cores and ejected by stellar winds and supernova explosions, wandering through the galaxy for billions of years before ending up in the instruments of a probe launched from Earth. The approach to silence is gradual. Each instrument that goes offline on the Voyager 1 represents not only a reduction in data returned, but the closing of a scientific window that will not reopen until, if ever, a successor mission reaches the same region of space. The cosmic ray subsystem going offline would end the continuous record of galactic cosmic ray flux in interstellar space that has been running since 1977. The magnetometer going offline would end the direct measurement of the interstellar magnetic field at an increasing distance from the heliopause. Each closure is a small ending, a door shutting on a room that human science entered for the first time and has been exploring with aging instruments and dwindling power. The scientists who have been receiving these data packets understand the significance of each shutdown. There is a peculiar grief in it, not for a person, but for knowledge. The data that would have been returned by the instruments that shut down too early will never exist. The interstellar medium in those energy ranges, at those distances, in that direction, will remain unmeasured until another mission reaches it. And when another mission reaches it, the scientists who worked on Voyager will mostly no longer be here to see it. Consider what the engineers at JPL achieved when they designed Voyager. They built a spacecraft in the early 1970s that had to survive for decades in deep space, in conditions of extreme cold and radiation that had never been directly measured, powered by a fuel source that would not exhaust for half a century. carrying scientific instruments calibrated for a range of environments from Jupiter's intense radiation belts to the tenuous reaches of interstellar space, all communicating through a radio transmitter that would need to maintain a functioning signal across distances that grew by 600 million kilometers every year. They did not have access to any of the design tools or computational resources that modern aerospace engineers use routinely. The processors aboard Voyager 1 operate at 0.00006 GHz and have approximately 68 kilobytes of memory. The smartphones that people carry in their pockets today are many millions of times more powerful, and yet the Voyager design has outlasted every prediction of its operational lifetime. It has travelled farther than any other human-made object. It has crossed a boundary that was theorised but unmeasured when it launched. And the instruments built by those engineers in the 1970s have delivered calibration-quality data about interstellar space from a location 22 light-hours away, returning discoveries that textbooks are still incorporating. There is a principle in science that a boundary, when understood well, illuminates what lies on both sides of it. The heliopause is no exception. By measuring the properties of the heliosphere at its outer edge, scientists have gained insight into the heliosphere's interior that could not be obtained any other way. The pressure balance at the heliopause constrains the total momentum flux of the solar wind integrated over the entire heliosphere, which provides a measurement of the solar wind's properties averaged over a much longer time and larger spatial extent than any in situ measurement near the Sun. The cosmic ray population just outside the heliopause tells us what the interstellar cosmic ray environment looked like before the heliosphere filtered it, providing the baseline against which the heliosphere's filtering efficiency can be measured. The interstellar magnetic field direction, measured at the boundary, places constraints on the orientation of the heliosphere's tail and the geometry of the hydrogen wall visible from Earth by Hubble. Every measurement made by Voyager at and beyond the heliopause has sent information backward through the models, refining the picture not just of the boundary but of the entire interior of the solar system's magnetic bubble. From Voyager 1's current position in interstellar space, the galaxy looks different than it does from inside the heliosphere. Not dramatically different, not in a way that would be obvious to a human observer, because the heliosphere is so small relative to the galaxy that moving from inside it to just outside it is, in galactic terms, a displacement too small to measure. The stars in the sky from Voyager's position are in exactly the same positions to any precision that matters as they would be from Earth. The Milky Way's band of light stretches across the sky in exactly the same configuration. The cosmic microwave background, the afterglow of the Big Bang, fills the sky with the same nearly uniform microwave glow in every direction. What is different is the particle environment. The galactic cosmic rays are slightly more abundant in interstellar space than inside the heliosphere. The solar wind is absent, replaced by the quiet drift of the interstellar plasma. The specific mix of energetic particles is slightly different. These differences are real, measurable, scientifically significant. But from the perspective of the universe as a whole, Voyager 1 has not gone very far. It has crossed the edge of one small star's domain. The rest of the galaxy, 100,000 light-years of it, begins immediately beyond. So what did NASA actually detect where the Sun's influence ends? They detected a sharp transition in plasma density, from roughly 0.0006 particles per cubic centimetre inside the heliosphere to approximately 0.08 per cubic centimetre outside it. They detected a sudden drop in anomalous cosmic ray intensity and a corresponding rise in galactic cosmic ray intensity. They detected a shift in the magnetic field direction of approximately 40 degrees, reflecting the transition from the Sun's Parker spiral field to the local interstellar magnetic field. They detected a thin boundary layer, just a few astronomical units thick, separating two environments with distinctly different plasma temperatures. They detected a stagnation region just inside the boundary where the solar wind slows nearly to a halt before deflecting sideways. They detected a magnetic highway region where field lines connected the two environments before the final boundary was crossed. They detected plasma oscillations at a frequency corresponding to interstellar electron densities that confirmed, with mathematical certainty, that the spacecraft was in a region the Sun no longer controlled. In total, they confirmed that the heliosphere is a real, physical, bounded structure with measurable properties, and they delivered the first direct measurements of what interstellar space looks like when you're actually in it. What remains unknown, even after Voyager's historic crossings, is in some ways more significant than what is known. The exact shape of the heliosphere, particularly the heliotail, is still unresolved. Whether the heliosphere is comet-shaped or croissant-shaped matters for understanding how effectively it shields the planets from galactic cosmic rays over time. The mechanisms of particle acceleration in the heliosheath and at the heliopause are not fully understood. The structure of the boundary layer at the heliopause, the detailed physics of magnetic reconnection occurring there continuously, is known only at two sampling points: the interaction between the heliosphere and the interstellar neutral hydrogen that drifts through the heliopause and fills the inner heliosphere is measured but not fully modelled. Each of these unknowns is not a failure of the Voyager mission. They are the legacy it has left for the next generation of measurements. The scientific questions that Voyager opened at the heliopause are more interesting, more specific, and more tractable than the questions that existed before it crossed. That is the mark of a successful scientific mission, not that it answered everything, but that it created better questions. The heliopause crossings have had ripple effects throughout heliophysics and beyond. The models of other stellar astrospheres have been recalibrated based on the measurements from Voyager's crossings. The interpretation of Hubble's observations of hydrogen walls around nearby stars has been refined using the plasma density and magnetic field data from the in situ measurements. The theoretical understanding of the termination shock and particle acceleration in the heliosheath has been revised multiple times in the decade since the first crossing, each revision incorporating the constraints provided by the actual measured data rather than theoretical prediction alone. The community working on the origin and propagation of galactic cosmic rays has updated its models of the local cosmic ray environment using the flux measurements from beyond the heliopause. The scientists thinking about habitability in other star systems have incorporated the heliosphere measured shielding efficiency into their models of what living conditions would be like on planets orbiting different types of stars. One spacecraft, launched before the internet existed, carrying instruments designed before personal computers existed, has in the span of a decade reshaped scientific thinking in multiple separate fields of research. We began at the edge of everything the Sun controls, a spacecraft, 22 light-hours distant, transmitting at 22 watts, relaying data across 18 billion kilometers of space to antennas in California and Spain and Australia. We have traced the story from Eugene Parker's rejected paper in 1958 through the confirmation of the solar wind, through the design of a spacecraft to catch a once-in-175-year alignment of the outer planets, through the termination shock crossing and the heliosheath and the magnetic highway, and the final clean permanent transition on August 25, 2012. We have held the plasma densities and the magnetic field angles and the cosmic ray counts, and we have tried to understand what they mean, not just as data but as facts about the structure of the place we live. The heliosphere is real. Its boundary is real. We have touched it. We have instruments sitting in it right now, still sending home their readings, still measuring the interstellar medium for as long as the plutonium holds out and the antennas can find the signal. What the heliopause gives us, beyond the data and the scientific understanding, is a sense of proportion. We live inside a bubble. The bubble is vast by any human measure, extending to 4 times the distance of the most distant planet. And yet it is a microscopic irregularity in the interstellar medium, a small sphere of stellar influence surrounded by the vast, ancient, continuous fabric of the galaxy. Knowing this does not make the interior of the bubble less meaningful. It makes it more so. The Sun has been maintaining this bubble for 4 billion years, pouring energy outward continuously, creating and sustaining the protected environment inside which the chemistry of life was able to proceed. Every drop of water that has ever pooled on Earth's surface, every molecule of DNA that has ever replicated, every breath ever drawn by any living thing has happened inside this ancient, persistent, solar-made shelter. The boundary matters because the interior matters, and the interior matters because it is where, against considerable odds, something remarkable happened. Life, mind, curiosity, enough curiosity to build a machine and send it to the edge just to see what was there. Right now, as you rest, Voyager 1 is moving outward at 17 kilometers per second. It had been moving for more than 48 years without pause, without steering, without human hands on its controls, guided by the same physics that guides every particle in the universe. Somewhere in the dark between the stars, on a course no one before 1977 had ever travelled, it is still there, still transmitting. The signal it sends home is quieter than a whisper. In across the sphere of light hours it has travelled, collected by dishes as large as a city block, decoded by software on machines that did not exist when the spacecraft launched. And in that signal, in those few hundred bits per second, is the report from the edge of the solar system, from the boundary of the Sun's ancient domain, from the threshold of everything the universe has placed beyond our reach so far. We built something that crossed that threshold. We are reading what it found, and in the reading of it, in the decoding of each fragment of data from the interstellar medium, something that began 4.6 billion years ago in a collapsing cloud of interstellar gas has arrived, quietly, at the ability to understand itself. Rest now. The signal is still coming, and somewhere in the dark, 2 hours away, the spacecraft continues its ancient, patient journey into the uncharted deep.